We have studied how to analyze relationship, and we looked at correlation and linear regression and multiple regression. Now, the second topic of this module is hypothesis testing. Hypothesis testing determines the relationship between two variables or more than that. We usually start with hypothesis testing to analyze a process. So it is important for us to know how to conduct hypothesis testing. In hypothesis testing, we have to look at first whether it is a mean test or proportion test. You can test or compare the means of some samples. For example, the efficiency, the average efficiency of a process for assembly line 1 and assembly line 2. You are comparing them together. At the time, you are looking at mean, right? Or you can talk about proportion. That is the percentage of the people working at 100% of quality at assembly line 1 and assembly line 2. You are at the time comparing proportion. In that case, the formula that you are using can be different. If you determine mean and proportion, the next thing that you can do is how many samples you are using. Is it one sample or two samples? As I just mentioned, if you're looking at only one assembly line, for example, it could be one sample test. If you are comparing that with another line, that could be two sample test. If it is more than two samples, then you're going to use ANOVA test for that. So depending on that characteristics, we are going to have this different formula. If it's one sample test, then we are going to use z equals x bar minus mu over sigma over square root of n. That's a one sample mean test. If it is one sample proportion test, then we write as pi equals value, or pi does not equal to a value. That's how you formulate the null hypothesis and alternative hypothesis. Then you use this formula, which is z equals p minus pi over square root of pi, parenthesis 1 minus pi, close the parenthesis, divided by n, the sample size, and that is the formula, a little bit more complicated. If it is two sample test, then the hypothesis looks like mu of sample A is less than equal to mu of sample B. And alternative hypothesis, the opposite of this sign. So mu sample 1 is greater than mu sample B. And the formula is also a little bit complicated. That's z equals x1 bar, sample 1 mean, minus x2 bar, sample mean 2, right? And divided by the standard deviation, taking the sample size into consideration. So square root of s1 square over n1 plus s2 square over n2 will be the formula for the mean test, two sample mean test. If it's two sample proportion test, then you are going to be using this null hypothesis and alternative hypothesis. So pi 1 is less than equal to pi 2, and alternative to that is pi 1 is greater than pi 2. And the formula is much more complicated. Z equals pi 1 proportion 1 minus proportion 2. So the proportion of sample 1 minus proportion of sample 2 divided by square root of PC 1 minus PC over N1 plus PC 1 minus PC over N2. Here PC means pooled proportion. That is defined by x1 plus x2 over n1 plus n2. So that's the more complicated version of proportion test for two samples. If you have more than two samples, at the time you're going to be using ANOVA rather than this formula. Here are five-step process that we want to follow when conducting hypothesis test. First step is defining the hypothesis. We want to define the hypothesis, whether it is a mean test or proportion test. If it is mean test, we use mu. If it is a proportion test, we use pi. Second step is define the statistics, and that's explained from the previous slide. that depending on the type of the hypothesis, we are going to use different statistic formula. The third is define the rejection region. Where is the rejection region that we are going to be using for? And fourth is calculating the statistic. Fifth one is drawing conclusion. And again, here's the formula that we are going to be using for step two, whether it is one sample mean test or two sample mean test, or one sample proportion test or two sample proportion test. We have to look at it. And if it is more than two samples, then it's going to be a more ANOVA test. Let's take a look at this example together. Rowan Steel Company manufactures and assembles desks and other office equipment. The weekly production of the Model A325 desk at the Fredonia plant follows the normal probability distribution with a mean of 200 and a standard deviation of 16. Recently, new production methods have been introduced and new employees hired. The VP of manufacturing would like to investigate whether there has been a change in the weekly production of the Model A325 desk, and a sample of 50 was gathered and the mean was 203.5. So let's first conduct, by the way, this is not two sample test, but population mean test. So first step is stating the hypothesis, defining the hypothesis. And our interest is to find whether there was a change in means after adopting this new process. And therefore, null hypothesis mu is 200, meaning that there was no change. And alternative hypothesis mu does not equal to 200. So it implies that there was a change, whether it's positive or negative. Step 2, select the level of significance. Use alpha equals 0.01 if there's no mention of it in the problem statement. Third step is selecting the test statistic. And we know that this is one sample mean test. Therefore, we choose z equals x bar minus mu over sigma over square root of n. That is the formula that we're going to use. Then fourth step is formulate the decision rule. And we say reject null hypothesis if z absolute value of z is greater than z alpha over 2, right? So z alpha over 2 is given, or we can find it from the z table, and absolute value of z means that, or implies that this is a two sample and two-tailed test. So let us plug the data into the formula. Then what we find is the x bar is 203.5. The sample mean that we find is 203.5 right here. And mu, we are assuming mu is 200. There's a change or not, right? That was the mu. So put that here, 200. And sigma is found as 16, right? It's given over here. The standard deviation of the population is given as 16, so we put that here. And we also find that the sample of 50, so number of sample is 50, so you put it into the formula right here, and then you get 1.55. And z alpha over 2, or z alpha is given as 0.01, so z 0.05, meaning this this is 5% and this shaded area is 5%. And if you look up the table, then you will see that it's negative 2.58 and positive 2.58. So if your z value is greater than either 2.58 or less than negative 2.58, then you are going to reject the null hypothesis. However, you find that your statistic is actually 1.55, which is less than the statistic z alpha over 2, z 0.05, that is 2.58. And this one does not fall into the rejection region. So therefore, your conclusion is fail to reject the null hypothesis. Therefore, your conclusion will be because 1.55 does not fall into the rejection region, null hypothesis is not rejected. There is insufficient evidence to state that the production rate at the plant has changed from 200 per week, right? So that is the conclusion. So by looking at the problem statement itself, you may think that, oh, there was no change, or there might have been a change, but is it statistically significant change or not? That has to be determined. And at after this calculation, we find that it is there is no or there is insufficient evidence to state that. Let's also take a look at a two-sample mean test. In a two-sample mean test, let's see this new example. Let me read it for you. The U-Scan facility was recently installed at the Burn Road Food Town location. The store manager would like to know if the mean checkout time using the standard checkout method is longer than using the U-Scan. She gathered the following sample information. The time is measured from when the customer enters the line until their bags are in the cart. Hence, the time includes both waiting in line and checking out. The standard deviation for standard type is zero point 0.4 minutes, while that for UScan is zero point 0.3 minutes. So the question that we want to answer is, was there a change after adopting these two different type of scanning system? And we find that the average mean for standard scanning is 5.5 minutes, and for new scanning system, 5.3 minutes. So we see that at least 20 seconds were reduced after adopting new scan. And the standard deviation was zero point 0.4 for standard scanning system and zero point 0.3 for U-scan system. And the sample size was 50 for standard and 100 for U-scan. So using this, can we say that there's a statistically meaningful change in this relationship? And by conducting two sample mean tests, because we are talking about a sample mean, and we have two samples, and the sample size is greater than 30, so we can use a two sample mean test and see if that is true. So step one, state the null hypothesis and alternative hypothesis. Null hypothesis, notice that we have two samples, therefore we used two mu's. Mu for S-scan system or standard system, and U for U-scan system. And we think that the standard system um, will take shorter than the U-scan system. An alternative hypothesis is the opposite of that. You think that standard system is taking longer than new system, which is U-scan, right? So if you reject the null hypothesis, you prove that alternative hypothesis, meaning the new scanning system is taking shorter than the standard system. Step two is selecting the level of significance. If there's no mention of alpha level or significance level, we use zero point zero 0.01. And in this case, let's assume that. And the third one is we want to determine the appropriate test statistics. And as we stated here, it's a mean test and two samples are there. Therefore, we choose two sample mean test, and z equals x1 bar minus x2 bar over square root of s1 squared over n1 plus x2 squared over n2. Step 4, formulate the decision rule. Reject null hypothesis if z is greater than z alpha, and that is z is greater than 2.33, right? So 2.33 is right here, and z is greater than that. Then you're going to reject the null hypothesis, meaning that the new U-scan system is its efficiency is better than standard system. So plug the numbers that we found from the previous slide into this formula, then we get 3.13. 3.13 falls into this rejection area, right? It's right tail test, and the graded area is the rejection area, and we see that it's falling into this rejection area. Therefore, what's the conclusion? You rejected the null hypothesis, meaning that the U-scan system is taking shorter than standard system. So the decision is reject the null hypothesis because z is greater than 2.33. There is sufficient evidence that the mean checkout time using the standard checkout method is longer than using the UScan system. That's how you are going to solve the two sample mean test. And you similarly, you can apply the same method for one sample proportion test or two sample proportion test. Let's go over a few questions together. Which of the following is a valid null hypothesis? A, P is greater than 1 over 8. B, mu is less than 98. C is the mean of population A is not equal to the mean of population B. And D is mu equals 110. What do you think? The answer is D, mu is 110. This is one sample mean test. And C is pretty close. However, um, uh, it's a worthy here in this case. And B is mu is less than 98. Usually, null hypothesis includes equal sign. So, if you don't have equal sign in the statement, that means it goes to alternative hypothesis. That's why B is not the answer. So the answer is D. Here's another question. Determine whether the following two types of rockets have significantly different variances at the 5% level. Assume that the larger variance goes in the numerator. So rocket A, rocket B. So this is um, on a F test actually. So it's more challenging that I did not cover this one. So when you are comparing variances, you have to use F test. So null hypothesis in this case is the variance of rocket A uh, equals to variance of rocket B, and null alternative hypothesis is that their variances do not equal to each other. And you have to calculate the F table S1 square over S2 square, and it is a two-tailed test, and you put a variance into the formula, which is F30, 50, and 0.025 because it's a alpha is 5% and it's a two-tailed test. You have to divide it by 2, so alpha is 0.025, and you look up the table, then you get 1.82. Uh, the actual F value that you calculate is uh, the variance over the other variance. So 2.237 is greater, so it goes to numerator, and 1.347 is it goes to the denominator. And if you calculate that, it's going to be 1.66. So F value 1.66, and the rejection area is 1.82, and it's less than 1.82. Therefore, you fail to reject the null hypothesis. So the answer is B, no significant difference because FCalc is less than FTable. Let's tackle this question together. In an experiment designed to compare two different ways of measuring a given quantity, it was desired to test the null hypothesis that the means were equal at the zero point zero 0.05 level of significance. A sample of 5 parts was measured by method A and a sample of 7 parts with method B. A ratio of 2.179 was obtained. Now, one should what, right? So in this case, the degree of freedom is n1 plus n2 minus 2, and degree of freedom is 10, therefore. Um, and t-value is point, uh, when you're finding the t-value from the t-table, you have to look at alpha level 0.025 because it is zero point zero 0.05 level of significance and it's two-tailed, so you have to divide by 2, and the sample size is 10, and you get 2.228. And you see that the t ratio calculated from the sample was 2.179, and we see 2.179 is less than the rejection region, t equals 2.228. Therefore, we fail to reject the null hypothesis. So the answer is fail to reject the null hypothesis. The last question, in order to test whether the average output of one machine is the same or greater value than another machine, a sample of 10 pieces was taken from each. The calculated t-value turned out to be 1.767. Using a one-tailed test with a significance level of 0.05, one concludes that A, the obtained t ratio does not fail within the critical region. B, there was no significant difference between the means. C, the null hypothesis was rejected. D, the null hypothesis was accepted. The answer is the null hypothesis was rejected. The null, we have to follow this five-step procedure. So if we define the hypothesis, null hypothesis is mu 1 equals greater than mu 2, and the mu alternative hypothesis is opposite of that. Mu 1 is less than mu 2. And you want to find the degree of freedom, which is n1, number of sample for sample 1, and n2, the number of sample 2 minus 2, because we use the two samples. And then you get 18. And we want to find the t-value for that. And this is one-tailed test, so you don't have to divide this alpha by 2. So you use 0.05 as it is. So t 0.05, comma 18 samples, and you go back to the t table in the textbook and read it, then you get 1.734. And the t calculated value here is given as 1.767. 1.6767 is greater than 1.734, which is the rejection t value. Therefore, we reject the null hypothesis. Okay, so in module 3, we have learned how to analyze relationship using correlation and simple linear regression and multiple linear regression. And we also learned how to do hypothesis testing, and depending on the number of samples and whether it is a mean or proportion test. And we have to follow this five-step procedure to do that. Thank you.